looked into this so-called unit theorem that characterizes the property of a DP algebra to be when viewed as an object of its compact derived category, at least a plus or tilting object, in terms of certain invertibility property of its so-called restricted universal massive product, which is this class A over star. I now unfortunately wrote brace again instead of point brackets. Let me correct that actually. Somehow using macros is a little bit easier than remembering which symbol you want to write. Yes, so this is the restricted universal massive product of the algebra, and we saw that, well, it corresponds to a map in the stable modular category of bimodules for lambda, and it's supposed to represent an isomorphism between the simple second cyclicity of lambda as a bimodule and this twisted bimodule induced by the choice of some automorphs. Okay. And therefore we saw that this restricted universal mass product is a proof that lambda, the endomorphism algebra of a twisted this causating object is twisted periodic as it needs to be the case. So today I'm going to try to sketch some of the ideas that go behind actually the injectivity of the correspondence. So I try to motivate it by looking at the surjectivity of the correspondence, and I will not explain so much about that, but the tools that we use are the same. So this will maybe compensate for that. So we want to know how to use this invertibility condition. So for this, another reminder, so the Hodgkin cochain complex of straight algebra lambda has more operators, so has a cup product, which in homology corresponds to the Yoneda product of extension. So the cup product. P U lambda C lambda. So this is by degree 0, 0, D plus R, D plus S is given by G tensor F being sent to the multiplication, and then in position 1, I compose with G, and then G has P inputs. So in position P plus 1, I compose with F, and then I need to multiply by -1 to the total degree of G minus 1. So this looks as follows. So there is a binary operation, and then I take G and F. Plug here, so here I have P inputs. So after I plug in an input 1, then to plug in F, I need to plug in input P plus 1. Yeah, that's just. But this is the thing that you would like to write down. This can also be written in terms of the brace operations. So using that, and the invertibility condition on lambda, one can prove the following. So proposition, just get the indices the way I want it. Right. So now there are more and more indices. So more and more indices. Yes. So with A as above, and such that A is DC, is positive tilting, is a positive tilting in its perfect derived category, so that I have this equivalent condition 2. The maps given by cup product take this vertical degree arbitrary. We only need this when this degree is minus P anyway. So I can now take the cup product with the universal massive product of A. So this map is bijective, is bijective for P bigger or equal to 2 and surjective for P bigger for P equals to 1. Okay, so that is something one can check. This is also both in a case equals to 1 already used by Fernando in his first paper for the case equals to 1, and this is now just a straightforward modification of that one can get this. So we see that it implies now some condition about some map between Hochschild homologies of this graded algebra. Remember here we always view now lambda as a graded algebra. And we are just remembering its universal massive product. So not. So we want to now explain how to leverage this. And well, now somebody will need to remind me if this is section 7 or 8. Yeah. Yes. 7. Okay. Thank you. So I will introduce another invariant called the Hochschild-Massey homology. That would be what we would use to prove the injectivity of the correspondence we're interested in. So lambda is now these bars graded algebra for some fixed t bigger than or equal to 1 as usual. So in particular, as usual, I mean, because not that you're disappointed that this is all like about sparse algebras. In the case d equals to 1, it applies to all graded algebras, right? This is question. Definition. So a Massey algebra structure on lambda is a class. We'll write md plus 2 class of pi degree d plus 2 minus d, just as it would be the universal massive product of some putative minimal A infinity structure on this graded algebra lambda that I do not assume yet it exists, so it's not needed for this definition. So I need Hochschild class of this pi degree, and it shouldn't be arbitrary because we know that the universal massive product satisfies the additional condition that it's less than half a square. So this is a Hochschild class of the sort of correct by degree to have come from the first possibly non-trivial Heidegger operation in a minimal A infinity algebra structure on lambda that has the same additional property. Okay, so given so my ins is right, yeah, so p return, okay, that's okay. So the Hochschild Massey complex of the pair lambda and this class, this massive algebra, is fine total. So it's given, so its components are their actual Hochschild cohomologies. Of the graded algebra lambda, and only consider this for p equal bigger and equal to 2 in Q an integer. Yeah. So the cohomologies of the complex are, sorry, the components of the complex are the Hochschild cohomologies of lambda already as a greater algebra. This endowed with the Hochschild massive differential so now I use the Gerstenhaber bracket in Hochschild cohomology to define differential Hochschild massive to be in complete analogy with the Hochschild differential as the bracket with this class that gives this great algebra lambda the structure of a massive algebra. And this is now this is right. Yeah. So this is by degree d plus 1 minus d, because this class has by degree d plus 2 minus d. And when I do brackets, I lose one input. So this is responsible for this minus 1. Okay. Yes. So if you remember, at the cochain level, the Gerstenhaber square is defined as the brace with a class with a cochain with itself. And we saw, I mean, I hinted at that the reason why the Hochschild differential squares to 0 was because of the associativity of the multiplication that we couldn't code in terms of m brace m or m2 brace m2 being 0. So here is similar. And I should say here now, actually, that I want to assume that the characteristic of K is different from 2 for simplicity. Otherwise, in a 1 by degree, I need to change the formula. It's not important. It all can be done in characteristic 2. Everything remains valid, but just for simplicity. Yes, and of course the. Oh, then I moved the wrong black hole. Homology of massive algebra. Well, is of course the cohomology of the Hochschild massive complex. So I'll mention just very briefly, I do not have any time to get into details about this, but if you wonder why one defined this complex, for this comment for those of you that know about spectral sequences, there is a certain extended Bousfield-Kahn spectral sequence that appears in this context. This is basically appearing in the d plus first page of the spectral sequence as the terms and the differential. Okay, so this is a computation one needs to make. Of course, as in when one defines a spectral sequence. And it will arise in relation to a certain obstruction theory that was developed by Fernando already to handle the case d equals to 1, and then unfortunately can be modified with not much work to hold in the disparse case as well. And I also mentioned that in another recent paper of ours, so together with Fernando this year, we have explained how to explain that obstruction theory to work also with A infinity bimodules or digibimodules as well, because you might remember the other theorem about the bimodal right Calabi Yau properties about deciding when the diagonal bimodule of to a shift is quasi-isomorphic to the dual of the diagonal bimodule. So you might want to have such a situation available as well. I mean, such an obstruction theory available as well for dealing with bimodules, and that's something we needed to do. But this is just to say that if this definition for you looks a little bit ad hoc, there is another part of the story that one could tell that makes this definition inevitable. Yeah?
which maybe good to know. Okay. So now, interestingly, so now we wanted to know how to use this invertibility property that we now have here. The surjectivity is actually just needed in the case of bimodules. Turns out this is what plays a role. The bijectivity is what will play a role in this case only. So an interesting observation that as many of the things we do in the general case, it's somehow implicit in Bernardo's work in case d equals to 1, maybe sometimes a little bit hidden in a proof and things like this. But there is an interesting thing that we can observe here is that, well, the cup product with this class so I need to add is a chain map with respect to the Hochschild differential of this pi degree. So this is total degree 2. Yeah. So it doesn't go horizontally; it goes a little bit skewed, if you want. So this is a chain map. So we have a canonical and sort of shifted endomorphism of our Hochschild-Massey complex, but this is in fact a null homotopic chain map with via the explicit null homotopy given by the cup product with another, sorry, I should write like this, with another class So this is now a homotopy of total degree 1. So 1 before the total degree 2. Hope I'm not touching this at some point. There is an implicit null homotopic given by cup product with the class of the so-called fractional Euler derivation. So this is this is given by x goes to x over dx. So this is a unary operation of degree 0 that sends an homogeneous element of the great algebra lambda to that element times its degree over d, and remark that this is an integer by virtue of the sparsity assumption. Yeah, so this is called the fractional Euler derivation. And well, one can check that this is a Hochschild cocycle, so it defines a class in Hochschild cohomology. I can take the cup product with that class, and using that the chain complex I'm interested in is given by the terms is the Hochschild cohomology already. then well, this is somehow a well-formed expression. And the fact that this is a chain map, for example, has something to do with the Gerstenhaber algebra structure of Homological cohomology, for example, for those of you who don't know what that means. It's a kind of compatible shifted graded algebra and graded commutative algebra structure. Suitable sense. And the fact that this is a null homotopy is a computation one can perform with this class, which has an explicit format. Yeah, so,
would you say, is this like from the spectral sequence perspective, would this be formal or not?
No, this class is special. So you can maybe axiomatize the situation a bit more. So in that paper that I mentioned on obstruction theory of infinity bimodules, we work with rather in a rather general situation, not just endomorphism operats, so not just Hochschild per chain complexes, so to say. And then many things are formal in that sense, that arise from an operatic context and a spectral sequence that one can define given enough structure. And yeah, I mean, you can just more or less axiomatize the existence of this null homotopy if you want. But this is, of course, not going to exist in general. Yeah, does that make sense?
Yeah, thanks.
Mm-hmm. Okay, so right, so this leads us to a theorem. So what I want you to observe here is, of course, this map is actually this map. Just replace the symbols, right? And just define this part, these things to be terms of my complex. So if I'm in the dz cluster tilting case, I know that I have a certain null so endomorphism, which is bijective in many degrees, but it's also null homotopic, right? So it will induce an isomorphism in certain cohomological degrees or pi degrees, right? Because it's in these degrees, I mean, as long as before and after you have this isomorphism, so maybe even one of them needs to be surjective, so you get an idea why this is enough. It induces an isomorphism, but it also induces the zero map because no homotopic. So it will imply that lots of cohomologies of this Hochschild-Massey type need to vanish. Yeah. So I get some. If I'm in this situation, thanks to this general observation, I have a lot of vanishing of Hochschild-Massey cohomologies. Mm-hmm. And yeah, using this, I mentioned this is actually the theorem B. So the Derived Auslander Iyama Correspondence is theorem A in our paper. This is theorem B, but I want to refer to this one now. It's theorem B. So the theorem is, for those of you that know, and I will actually explain, this is actually a consequence of our theorem as well. There is a theorem of Kadishvili called the intrinsic formality theorem. So if you know it, keep it in mind. This is a bit similar. So if I have A, these parts DG algebra, suppose that the Hochschild-Massey cohomology of the cohomology of A is, remember, it's just as a graded algebra. What we define all of this as a graded algebra, but induced with the induced Massey algebra structure. So I can consider this. So the cohomology of A is a graded algebra. It inherits a minimal A infinity algebra structure. I can take the universal Massey product for that minimal A infinity algebra structure, and I mentioned, didn't explain exactly why, but that this turns out to be independent on the choice of minimal model because of the invariance of this thing under gauge A infinity isomorphisms, etc. So this is somehow a well-defined invariant I can associate to A if I want to think in these terms. And if this vanishes for all P bigger than D, then I can conclude the following. Yeah, so for those of you that know spectral sequences can imagine that what is happening here, that this telling me some obstructions will vanish and so on. This is how the story works. But I now I will not anymore talk about that for today. Just so those that know that machinery should get maybe a feeling where this is happening. So then I can make the following statement. If B is a DG algebra such that the cohomology of B is isomorphic to the cohomology of A as graded algebras, then necessarily B is disparse. The cohomologically disparse. I mean, so of course not A disparse, but the cohomology I meant is disparse. Sorry about that. Where am I? If B is a DG algebra such that yes, so that these two great algebras are isomorphic, so I can identify them along this isomorphism, so that I can say that they have the same universal massive product equivalently under this isomorphism. The induced isomorphism in Homological cohomology sends the universal massive product of one to the one of the other. Yeah. So if you have this, then it is already the case that A and B are quasi-isomorphic. Yeah. And this is the kind of result that we would like to have, for example, to check the injectivity of the correspondence. Yeah. So I have the injectivity of the correspondence. I will have two DG algebras A that come from these at cluster tilting objects. And well, I would like to end up in a situation like this, right? Because I want to conclude that they're already quasi-isomorphic, right? It's the injectivity of the correspondence. But the problem in the formulation of the theorem is that I am not given any map of DG algebras between them, any zigzag of DG algebras between them, any A infinity morphism between their minimal models. I have no information about that a priori that I can use to check, well, this given map is a quasi-isomorph, right? So I would like to have, therefore, a theorem of this kind. Now, to give us an idea of how these things can be used, so I will explain how this theorem implies the classical intrinsic formality theorem of Calabi Yau. So here I will start with lambda graded algebra such that its Homological cohomology vanishes in degrees p bigger than or equal to 1. So here is p is strictly bigger than d. And here is p greater equal now d will be, you can imagine, we would use the theorem for d equals to 1. Then if B is a DG algebra such that the cohomology of B is isomorphic, I was going to write, which would be correct. No, the cohomology of lambda, but lambda is just a graded algebra of no dimension, so it's isomorphic to lambda as graded algebras. Then it is already the case that B is quasi-isomorphic to lambda, where lambda is viewed as a VGA with trivial or zero differential. So this is a so-called intrinsic formality theorem, because DG algebras that are quasi-isomorphic to their cohomology are called formal. And intrinsic formality that means that this greater algebra is intrinsically formal in the sense that any possible DG algebra with that homology is already formal. So there is no interesting promotion you can make of lambda to a DG algebra. It's already enough to consider lambda itself. So the proof is as follows. So we will use theorem B or B equals to 1. So this is, I do this also to emphasize that this theorem, even though it's formulated in the disparse case and might then look a bit special, it exists for D equals to 1 where it can be applied for arbitrary situation, provided you can verify this assumption. Yeah. So the assumption, so for P equals to 1, I have HH3 P plus, so 1 plus 2, 3, minus 1, lambda equals to 0. Means, well, implies, or means that 0 is, well, maybe that this, like this, is the only possible minimal mass algebra structure on lambda. That's where I use this thing. So this is, I don't even need to look for interesting mass algebra structures on this great algebra. I can't. And the assumption, so the vanishing assumption for P bigger than 1 will give me the desired, so I have by assumption vanishing of Homological cohomology of lambda. Sorry, I missed here the important by vertical 3 minus P. So I have this assumption, but I can now consider the function massive cohomology of the curve lambda 0, right? Which is defined, it's probably still here. Is it? Yeah, here. As terms function cohomology with 0 differential, so the cohomology is itself. So I have this. So I have 0. So by theorem B, so I don't need to check also. This comment is now important because I need to check the agreement of universal massive products, right? But this is a statement in the cohomology of P. So now I want to see P as the cohomology of P as a massive algebra, right? There's no, right? So there's no space for this guy. It's also 0. So by theorem B, we have what's now P quasi-isomorphic. So, well, this I also explained this to show maybe a point of view on this kind of theorem that is related to the comment I made maybe the second lecture. So this theorem can be thought of as an, I don't know what is the best way to say this, like the best adjectives, but it's some kind of almost formality theorem, yeah? In the sense that the quasi-isomorphism type of A is uniquely determined by its cohomology plus a minimal amount of algebraic data. In that sense, it's like an almost formality. It doesn't mean the A is formal in any way or almost formal in any way, but I regard this as being what I said, that an algebra being determined by its homology. So this will happen in terms of formality. A DGA is uniquely determined precisely by its homology. It is close to formality, but then A is going to be very much non-formal. Yeah, because in general, in order to have this bijectivity assumptions, in our cases, this will live in a non-zero vector space and so on. So we will not have a trivial universal massive product. This one can check very easily. In the cluster tilting case, it only happens when this lambda is semi-simple. So in very rare occasions. So one definitely wants to have such a little bit, well, I don't know how far, but it's a little bit more general statement than Kadeshvili is.
Is it possible to somehow indicate where you get this map from A to B from, given this?
From the obstruction theory. So the idea is that you don't do this for DG algebras, you do this for minimal A infinity algebras because you look at the minimal models. And then you look, so you work in the category of differential graded operands, where there is an operand called the A infinity operand, and maps out of the A infinity operand to the endomorphism operand of chain complex or a graded vector space in code. So they are in bijection with, almost tautological bijection with A infinity algebra structures. And what goes behind this is to understand, well, when two maps. So it turns out that two A infinity algebra structures on the same minimal A infinity algebra structures on the same graded algebra to be gauge A infinity isomorphic is the same as these two maps being homotopic with regards to a natural model structure on the category of DG operands. And then it is like a type of analysis that is very common for homotopy theorists to try to understand what are the obstructions, for example, for a map to be two maps to be homotopic, and this is how this works. Yeah, so it's something like you try to lift the isomorphism at the cohomological level and to find the higher components of the infinity morphism that you need, and there are obstructions for these components to exist, and there is a machinery from certain obstruction theory that tells you when these obstructions could, what are the obstructions for this existence, and so on, and you check that this is. This implies certain vanishing of certain things, and then this is how you proceed. It's a little bit, I mean, I consider whether I should speak about this more in detail in the lecture series, but I don't know, it's possible that not everybody is comfortable with spectrum sequences and obstruction theory, so about that one can give a lecture series, I believe, for people that have never heard of that. So I thought it was a little bit much, but maybe this gives them the opportunity to comment also on the surjectivity of the correspondence, because in that case one can consider maps from there is also truncated A infinity operand called AN operand, where you encode the existence of A infinity structures but on operations onto a certain level, and now your task is to extend this map to a, like the map that classifies this structure. You want to lift it to So the A infinity operator is filtered by suboperands, by the choosing how many operations you want to have, and it's a kind of typical extension problem also for homotopy theorists. That's why the same techniques appear, but there the difference is that let's just leave it like that. Yeah. So does that answer your question in some way? Maybe.
Yeah. I think so.
Maybe let's just say that one uses one of the many good ideas in homotopy theory to sort of produce a map, kind of, to exhibit the existence of a map out of thin air in some sense, like from little, from almost, from very little. Yeah. Is that, okay. Okay. So maybe I'll actually maybe mention something about this. Is this reasonable to divide this? So I want to now sketch. I will explain more carefully. Sketch of proof of the injectivity of the derived Auslander Iyama Correspondence. Okay. So we have A and B. So these are, and this is the injectivity of the map from 1 all the way to 3. Okay. So I will explain what this means because I don't necessarily expect that you remember what is 1, what is 3, and so on, right? So I have two DG algebras that are whose homologies are degree wise finite dimensional and such that A is the basic D-set cluster tilting object of its perfect derived category, and so that the same statement is true for B. So this means that the algebras A and B fit in the class of objects in item 1. Yeah? Now, the statement that A and B, so now I assume that A is going to be sent in equivalent terms to the cohomology of A as an algebra in degree 0 and the minus D homology of A as a bimodule over the degree 0 part. I explained that this is in a suitable sense equivalent to the automorphism sigma. And this, as before, it will be basic. Right? And I'm asking that these are in the same equivalence class. By design, and in the setup, as I explained how we could recover the whole cohomology of A from the degree 0 cohomology and the minus D cohomology as a bimodule of the degree 0 part, this implies that the cohomologies of A and B are isomorphic as graded algebras. So, because we want to apply this theorem, well, basically up to here, we're okay. Because I already explained that this vanishing comes immediately from this many times isomorphism that is null homotopic. So this first part we sort of have covered. And now there is the question about the agreement of the universal massive products. So if we regard this isomorphism as an identification, we have the universal massive products of the restricted universal massive products of A and of B that they live now according to the previous notation in the same space. Corresponding sigma, you just try to fit, they don't want to fit in the cohomologies, too tight. And both yield isos in the stable category of bimodules between these bimodules. Now, using this, you can assume that so these are reduced by choices of minimal models of A and B, and then you can fix one of them, and you can so-called perturb the minimal model of say B in such a way that the universal massive products agree. the restricted universal mass products. So we can choose, we can change, let's say change maybe some kind of change of coordinates. Minimum model for B. So we may assume to obtain there's something in this approach. So this is really a sketch, right? I didn't explain all the ingredients, all the propositions, etc. But we can assume that they have the same restricted universal mass products. And then some Gerstenhaber algebra computations but yeah, it's remember correctly, also involving the fractional Euler derivation and several things, show that these classes that have this invertibility type properties admit a unique lift. So this is remembering the function homology of lambda with coefficients in the graded lambda as a bimodule. And I want to sort of lift it to the function homology of graded lambda with graded lambda as coefficients as well. Yeah. And as long as I require that the Gerstenhaber squares of the lifts are 0, the lift is unique. Maybe I should have written this and then Gerstenhaber algebra computations. So since both of those restricted universal mass products obviously come with a preferred lift, namely the actual universal mass products of A and B, then one shows that they are actually already equal. So these yields implies this vanishing of Gerstenhaber squares, Gerstenhaber squares yields that in fact the universal massive products are already equal, so that we are in the setup of theorem B and using another position circle, using the proposition we also have the required vanishing the Hochschild-Massey homology of, well, in this case, we will let's say the homology of A with, and now it doesn't matter which universal mass product I write, where they are the same, but I should, of course, in any case, write the one for A to apply the theorem. For P bigger than D, hence A and B are quasi-isomorphic. So this is the idea of how this strategy of proof works. The subjectivity is more involved, it really is. But well, I would say, but maybe this also gives you some intuition about this. It's like, I think one thing that for me was very enlightening of this working in this project with Fernando. So by the way, the ones that don't know, Fernando Moro is an algebraic topologist and homotopy theorist. So perhaps not surprising that these are the methods. And as I said, he already worked in the case equals to 1, and this is not surprising that these are the methods that were used to prove this kind of theorem. But something that for me was very, very enlightening was it really gave me a new perspective on being a decent cluster tilting object. So unfortunately, I erased this, but this proposition is a corollary of the unit theorem, which gives an equivalent characterization of being decent cluster tilting that for me was completely unexpected. Yeah? So this is not at all for me in any way obvious from the definition that this is a way to formulate what does it mean to be decent cluster tilting. And another thing we see now from the proof from a purely naive algebraic perspective is that the decent cluster tilting property is in some sense the strongest possible thing almost you could ever ask for, so that you can verify this vanishing, so to say, trivially, by means of this general observation of this null homotopic map. You basically say, well, I don't know it's null homotopic, let's ask that it's an isomorphism where it needs to be, and then I get this vanishing sort of for free, right? In general, I don't know that many cases, I mean, only variants of this case where one can verify such vanishing. So in the way, this is somehow the best possible case where one can, like, easiest possible case in some sense, where one can verify this theorem, but where the algebras are not formal. So this would be beyond Kadashvili's intrinsic formality theorem. And for me, this was very enlightening, as I said. I mean, I feel like I learned really something completely new about these cluster tilting objects to this kind of approach. So they're really very special kind of generators of compactly generated algebraic triangulated categories. I have about 7 minutes. Is that right?
Yes.
Yes. Let's make the decision here. Okay. Yes, so maybe I want to maybe elaborate a little bit on my remarks about the category of DG operands. So let's call this in section 8, right? Further remarks on the proof. So given the graded algebra lambda, we are interested in I will not make many definitions, but I hope this will be for some of you interesting that maybe know more about this. So there is the so-called endomorphism operand. This is a graded operand, and it has graded spaces of operations given by the, just write now compactly, this is the internal home for graded vector spaces. So this is multilinear operations of all possible degrees. And without the crazy sign, the operatic structure is given by this infinitesimal composition of position I and etc. So this explains why this sort of related to this context. And then one is interested in certain spaces Xn that are certain mapping spaces in a category, the model category of DG operands from the DG operand encoding AN+2 algebra structures to the endomorphism operand. Then because the A infinity operand is filtered by these are suboperands, when passing to mapping spaces, one obtains a tower. So for n, I'm interested in them like this: x0, x1, x2, the thing here is spaces. What it means whatever you want. Yeah. So maybe the way you want to compute the mapping space in a model category. Maybe it's a Kant complex. Maybe it's an object of some Dwyer-Kant localization. Yeah. So you use the Dwyer-Kant localization, and then it's an object of an infinity category of spaces in your preferred form. Yeah. So I have this xn, and then it turns out that so infinity is allowed. This corresponds to infinity algebra structures, and the space of infinity algebra structures is the homotopy limit. Of these spaces. So just the limit in the infinity category of such spaces that you prefer. No? Here we're using model categories, so this is the homotopy limit of this tower. So associated to this tower, there is a so-called Bausfield-Kant spectral sequence, which is a little bit weird. So you want to understand the homotopy groups of the limit of a tower in the terms of the homotopy group of the pieces of the tower. And the reason you want to do this is because I kind of hinted at the fact that the path-connected component, so just pi zero of this space, is the gauge A infinity isomorphism classes of A infinity algebra structures on lambda. Minimal ones, because I chose this one to have a null differential. So I want to understand pi zero of this in terms of pi zero of the pieces. And for that, so this spectral sequence is a little bit strange because it's related to homotopy groups. So it has this kind of, the pages, they look like things like this, right? So it's a fringe spectral sequence where it's only defined in our convention around here. You have sets, or maybe even pointed sets, because to compute you need a marked point. So you have pointed sets, groups, abelian groups, and so on, just in analogy with homotopy groups, which pi zero is a set, pi one is a group, pi two in the higher abelian groups, etc. And what I want to advertise very, very briefly, because I think this is very important and I very rarely have time to advertise this, is that Fernando, so I really, really want to advertise the ideas of Fernando. I think this is really important in this project. So his previous work has been in this part and in the extension of the project so fundamental. He understood that in this case, you could extend this sequence and define it also in a certain part like this, using specific properties of this A infinity opera that we also leverage in our subsequent papers. And this so-called extent, so this line moves further as the pages go on and on and on. So at the end, it sort of converges to the Bausfield-Kant spectral sequence. But this allows you to define more differentials that would have been going to sort of empty parts. And this increases somehow the computational power of the spectral sequence in this specific case. And for example, it makes this Hochschild-Massey complex appear. Yeah, so this is quite interesting because, as I said, this is a spectral sequence somehow topological type, not algebraic type. Yeah, so this is a bit different, and they are a bit more difficult to work with. And basically, this, for those of you that know what it is, this vanishing of Hochschild-Massey cohomology that was here is needed to apply something called the complete convergence lemma of Bausfield and Kant, that allows you to decide when certain lim1 term in a so-called lim1 Milnor exact sequence vanishes, so that you can really check the type of thing that I was talking about. Yeah, so I mean that's how this works. So this is the key insight that you should really view. And maybe this is another that I will conclude with this. For maybe representation theories, it's a little bit surprising at first glance that to solve this kind of problem, one really needs to do homotopy theory. And in a way, the reason is because this is a problem about algebras, about quasi-isomorphism type of DG algebras, not about modules necessarily, right? And this means that, categories of modules are in general linear categories. Yeah, so sometimes there's pre-triangulated, stable, or whatever. But categories of algebras are not, right? And this is the case here. So we see that, but we need to look at this mapping spaces. This is not this mapping space is not a chain complex. Yeah, it's a mapping space. So this insight that one should look at things from this perspective is what allows you to solve this problem. Now, as a final remark, it turns out you can consider this for very general operands with multiplication, maybe endowed with an operatic ideal, etc., etc., etc. So this is something we develop in the obstruction theory for infinity bimodulus paper, because here you want to consider something called the linear endomorphism operand of the pair consisting of maybe, for example, lambda and b lambda or something like this. So this is an algebra and a bimodule, so to say. Yeah. So you want to understand compatible A infinity algebra structures and A infinity bimodule structures of one over the other. So you want to have this in very general terms, and the key insight is that it all depends on the good properties of this of A infinity operand with its filtration, and maybe some general graded operand with multiplication, and maybe some ideal and so on. This is enough. But then the story, once this is gone, part of the story can be repeated and part of the story needs to be sort of developed again. That's it. I conclude that.
If you have a general operand, so what's the kind of statement you have in mind for spectral sequence?
So you can define the something similar to the Hochschild cochain complex using your operand and the brace algebra structure, and you give yourself an operatic multiplication, which is some kind of like element of degree 2,0, such that brace of the element is 0. So you can model a lot of the things that give rise to Hochschild homology can be done very generally. In particular, it can be done with this kind of operand that we are interested in. And then you use this filtration so you look at maps from these things to your fixed operand, and then you get some similar tower with similar good properties. The thing is that, so what you need to do, so I guess you know how the Boswell-Kahn spectral sequence is defined is using homotopy groups of like fibers, right? And you want to maybe promote some of these fibers to be underlying spaces of some spectra, yeah, so that you can have more homotopy groups. So here you take some differences that are living in this range where things are well defined, and then you want to have some other range of definition where these things are negative. And then, yeah, this was already some of the insights of Fernando from the paper D equals to 1, that you can do such things. And that's how without that, you can still get the spectral sequence. But the important thing for us is the extension, and that the computations of the correct pages, so like for the first page, the differential, you want them to be given with the analog of Hochschild cochains and the Hochschild differential, and then by sparsity you can move all the way to the D plus first page, and you want to know that there everything is given as by, well, you need to assume something so that you can guarantee the existence of an analog of the universal massive product, right? Things like this.
So what kind of structure will you involve? If you talk to me as a homotopy theorist, like what kind of structures would I put on hold in that story?
A multiplication, an operatic multiplication. This should be graded. Maybe you want to have an ideal to have more generality, for some reason I can explain to you later. And you want to have a map that is defined in sufficiently large arity of the AN operand. So you might remember the computation of the fact that what should become the universal massive product is a cocycle, and the square zero relation, they depend on higher operations. So you need to have this map already defined a little bit sort of higher, so that you can prove that certain things are, etc., and then you can compute the differential that you need, and so on and so forth. Yeah. So this is so it is in a way quite general, and I can tell you why you need the operatic ideal if you want or interested later. Yes.
This Massey algebra stuff is very clearly motivated by the fact that you have a personal Massey algebra.
Yes.
Is there any sense in which you would use it when you don't have this universal Massey product? It's, from my understanding, in almost any case have, or when it's DG-graded. Yeah.
Yeah, so I can say I will try to interpret your question. So yes, you're right. In the DG setting, we are definitely always we always will have access to this universal massive product. And this is indeed a key invariant of our story. And in it's more like the way we approach the generalization is the other way around. We want to generalize this theorem, for example, to bimodule right Calabi Yau property. And the insight is more like, what do you need to have, as Gerd was asking, on your operand, so you can talk about the universal massive product and things like this. So it's more like the other way around. Like we want to keep having access to this because we wanted that this shows up in the computation of the differential of a page of a spectral sequence, something like this. Yeah. So it's more like that. But so yeah, I'm not sure what I would do if basically this invariant is my main insight to get started with the problem from this homotopical perspective.